We continue our study of vectors by now looking at the cross product. So let U be the vector U1, U2, U3. Let V be the vector V1, V2, V3. Then the cross product of U and V is the vector given by U cross V is equal to the vector U2, V3 minus U3, V2, negative quantity U1, V3 minus U3, V1, U1, V2 minus U2, V1. Since the result is a vector, this operation is also called the vector product. Now if we take a look at U dot U cross V, right, well, we're going to get U1 times the quantity of UV3 minus U3V2 minus U2 times the quantity U1V3 minus U3V1 plus U3 times the quantity of U1V2 minus U2V1. So we'll have U1 U2V3 minus U1 U3V2 minus U2 U1V3 plus U2 U3V1 plus U3 U1V2 minus U3 U2V1. The components that have a V3 are marked in green. The components that have a V2 are marked in blue. Terms that have a V1 are marked in yellow. Well, you can see that they will all cancel each other out, and so this dot product is 0. Well, this means that U is orthogonal to U cross V. In a similar manner, you can find that V dot U cross V is equal to 0. The actual calculation of this will be left to the viewer. Well, this means that V is also orthogonal to U cross V. And so we find that U cross V is orthogonal to both U and V. Now, calculating the cross product of two vectors is easier if we use the determinant of a 3 by 3 matrix. So there's no need to remember the formula given in the definition of the cross product. Now, matrices are studied more in depth in a linear algebra course. In this course, we will only introduce how to calculate a 2 by 2 and a 3 by 3 determinant. So first, determinant of a 2 by 2 matrix. So the determinant of the matrix A1, A2, B1, B2 is A1, B2 minus A2, B1. Notice what we did to calculate that determinant was we went across this way minus across that way. The technique that we're going to use in this course to evaluate a 3 by 3 determinant, A1, A2, A3, B1, B2, B3, C1, C2, C3, is such. Take the 1, 1 entry, the row 1, column 1 entry. Now cross out row 1, column 1. You're left with this matrix here. So you'll take A1, multiply it by the determinant of this matrix, B2, B3, C2, C3. And you'll do similar. This is a minus A2, then cross out second column, first row. You're left with the matrix B1, B3, C1, C3. And then plus A3, cross out third column, first row. Determinant of the matrix B1, B2, C1, C2. This method is known as the coefficient expansion, expansion. And again, this method is studied more in depth in a linear algebra class. So let's go ahead and evaluate this 3 by 3 determinant. So using the technique, cofactor expansion, 2 times the determinant of 1, 3, 3, 4. Right? Notice all I did here was I did this. There's the 2. So I crossed that out, and that's what I'm left with. Now it's minus times the determinant minus 1, 3, minus 2, 4. Again, notice all I did was there's 5. Then plus negative 1 times the determinant negative 1, 1, negative 2, 3. So this equals 2 times 1 times 4 minus 3 times 3 minus 5 times negative 1 times 4 minus 3 times negative 2 minus 1 times negative 1 times 3 minus 1 times negative 2. So 4 minus 9, negative 5, so we have negative 10 minus 10, right? Negative 4 plus 6 is 2 times negative 5, and then minus negative 1, so plus 1, and so our determinant is negative 19. So now the cross product calculation. Let U be U1I plus U2J plus U3K. Let V be V1I plus V2J plus V3K. Then U cross V is the determinant of the matrix IJK, U1, U2, U3, V1, V2, V3. So we'll go ahead and evaluate this cross product. Right, so we're going to have negative I plus 2J plus 5K crossed with 4I plus 0J minus 3K. So first row is IJK, second row negative 1, 2, 5. Third row is 4, 0, negative 3. So we'll get 2 times negative 3 minus 5 times 0, and that's I, minus, now we get negative 1 times negative 3 minus 5 times 4, and that's for J, plus negative 1 times 0 minus 2 times 4, and that is K. So our cross product is negative 6I plus 17J minus 8K. Putting it back in component form, we get negative 6, 17, and negative 8. So the direction of the cross product, direction of U cross V can be determined by the right-hand rule. So hold the right hand out with fingers pointing in the direction of U. Curl the fingers towards V, and the thumb will point in the direction of U cross V. This is summarized in this picture. Right hand, notice the fingers are originally pointing towards U. We then curl them towards the direction of V, and the thumb points upwards, which would be the direction of U cross V. So properties of the cross product. Let U, V, and W be vectors in space, and let C be a scalar. We have the anti-commutative property, which says that U cross V is equal to negative V cross U. We have the distributive property, which says that U cross V plus W is equal to U cross V plus U cross W. Multiplication by a constant, C times U cross V, this is similar to the dot product one, is CU all crossed with V, which is U crossed with CV. Any vector cross itself will give you the zero vector. And if you take U dot V cross W, it's the same as U cross V dotted with W. So the proof of property 1, U cross V. Well, let's factor out a negative from everything. So that'll flip all the orders. Right? So we'll have negative U3V minus U2V3. U3V1 minus U1V3. Then negative U2V1 minus U1V2. Well, now factor a negative completely out of that vector. Since all of these are real numbers, I can rewrite these in any way. So I'll eventually get negative the vector V2U3 minus V3U2, negative quantity V1U3 minus V3U1, and then V1U2 minus V2U1. But this here is V cross U. So now the proof of property 5, U dotted with V cross W. So we'll get U1 times quantity V2W3 minus V3W2 minus U2 times the quantity V1W3 minus V3W1 plus U3 times the quantity of V1W2 minus V2W1. Distributing everything through and grouping all terms that have similar W's. So we have U1 V2W3 minus U1 V3W2 minus U2 V1W3 plus U2 V3W1 plus U3 V1W2 minus U3 V2W1. Again, I grouped all the W1s together, all the W2s, and all the W3s. Out of this first grouping, we can factor out a W1. Second grouping, we can factor out a W2. Third grouping, we can factor out this W3. Well, this is U cross V dotted with W. Now let U be U1, U2, U3. Let V be V1, V2, V3. Let theta be the angle between them. Then if we take the norm of U cross V squared, right, remember that is just the first component squared plus the second component squared plus the third component squared. So if we expand this out, U2 squared V3 squared minus 2U2 U3 V2 V3 plus U3 squared V2 squared. So this is the expansion of this first group. Similarly, you can expand the second grouping and the third grouping. Now we add a U1 squared V1 squared u2 squared v1 squared. That should be a v2 squared. Oh, it's right here. This is the term I'm adding right here. u2 squared v2 squared. And I'm adding in a u3 squared v3 squared. But I can't just add them in, so I also subtract them. Now the reason for doing this is if you look at this first part here, so the part that's outside the parentheses, this is the quantity of u1 squared plus u2 squared plus u3 squared times the quantity of v1 squared plus v2 squared, v3 squared. What's in the parentheses is u1 v1 plus u2 v2 plus u3 v3 all squared. So this is the norm of u squared times the norm of v squared, right? So that's what this is. This is the norm of u squared. This is the norm of v squared. This is u dot v squared. So we get the norm of u squared times the norm of v squared minus u dot v squared we can write as norm of u squared times norm of v squared times cosine squared of theta. Or we can factor out that norm of u norm of v squared and be left with 1 minus cosine of theta, which is sine squared of theta. Now, since sine of theta is greater than or equal to 0, whenever theta is between 0 and pi, we get that the norm of u cross v is the norm of u times the norm of v times sine of theta. Now, let's find a unit vector that is orthogonal to both 5, 2, minus 1 and 0, minus 1, 4. Well, to find the orthogonal vector, what I'm going to do is say let u be 5, 2, minus 1, this is for simplicity, and v be 0, minus 1, 4. So a vector orthogonal to both of them, w would be u crossed with v. So we form our matrix. Now take the determinant. So we'll have minus 1 in the I direction, minus 20 minus 0 in the j direction, plus negative 5 minus 0 in the k direction. So it's 7i minus 20j minus 5k. Which I'll put in component form, so we have 7, negative 20, negative 5. And this is orthogonal to u and v. So now we just need to normalize it, because we want a normal vector. Well, that is 1 over the norm of u times w. So we get 1 over the square root of 49 plus 400 plus 25 times 7 minus 20 minus 5. So we wind up with 7 over the square root of 474 negative 20 over the square root of 474, and negative 5 over the square root of 474. And so there's our unit vector that is orthogonal to both v. So to evaluate triple scalar product, we can also use 3x3 determinants. So u, v, and w are vectors in space. Then u dot v cross w is simply the determinant of the 3x3 matrix formed, where the first row are the components of u, the second row are the components of v, and the third row are the components of w. So let's go ahead and use that technique to evaluate the triple scalar product u dot v cross w, where u is the vector 1, 3, 5, v is the vector 2, minus 1, 0, and w is the vector minus 3, 0, minus 1. So the first row is u, so it's 1, 3, 5. Second row is v, so 2, negative 1, 0. Third row is w, so negative 3, 0, negative 1. So we get 1 times 1 minus 0, minus 3 times negative 2 minus 0, plus 5 times 0 minus 3. So it's 1 plus 6 minus 15, and that is negative 8. So let's form a parallelogram that has adjacent sides u and v. Now let's suppose, furthermore, that u and v form an angle theta. Now note that the height of this would be the norm of v times sine of theta. So the area of a parallelogram is given by base times height, and so the area of this parallelogram would be the norm of u times the norm of v sine of theta. But that is the norm of u cross v. So if we locate vectors u and v such that they form adjacent sides of a parallelogram, then the area of the parallelogram is given by the norm of u cross v. So let P be 1, 0, 0, let Q be 0, 1, 0, and let R be 0, 0, 1, and these are the vertices of a triangle. And we want to find its area. So I'm going to create vectors U to be the directed line segment PQ, which in this case would be negative 1, 1, 0, and V be the directed line segment PR. So this is negative 1, 0, 1. Now, let's form a parallelogram that has the adjacent sides of U and V. Then, the area of this parallelogram is the norm of U cross V. So find U cross V. So we get 1 minus 0, negative minus 1 minus 0, and then 0 minus negative 1. So the area of the parallelogram is equal to the norm of that, which is the square root of 3. But the triangle is half base times height, right? Remember that? The area of the triangle is 1/2 base times height, and the area of the parallelogram was base times height. So our area of interest, the area of the triangle, is simply root 3 over 2. So now let's consider a parallelepiped that is formed with adjacent sides of u, v, and w. Now notice that the height of the parallelepiped will be given by the projection of u onto v cross w. So volume of the parallelepiped would be the area of the base times the height. Well, we already know what the base is. It's a parallelogram, and that has area of the norm of v cross w. So volume would be the projection of u onto v cross w, the norm of that, times the norm of v cross w. Well, that projection is u dot v cross w over norm of v cross w and its absolute value times the norm of v cross w. Well, norms are always positive, so these two wind up canceling each other out, and we're left with the absolute value of u dotted with v cross w. So we're going to find the volume of the parallelepiped with adjacent sides given by the vectors -1, -2, 1, 4, 3, 2, and 0, -5, -2. So the volume is u dotted with v cross w. And of course, we already saw how to evaluate the triple scalar. It's the determinant of the matrix whose first row is -1, -2, 1. Second row is 4, 3, 2. Third row is 0, -5, -2. And it's the absolute value of that. So we're going to have the absolute value of -1 times -6 plus 10 plus 2 times -8 minus 0 plus 1 times -20 minus 0. So this becomes the absolute value of -4 minus 16 minus 20, which is -40. So the volume is simply 40. So sometimes a force causes an object to rotate. So for example, turning a screwdriver or a wrench creates this kind of rotational effect called a torque. So the torque tau measures the tendency of a force to produce rotation about an axis of rotation. So this is the Greek letter tau. So let R be a vector with an initial point located on the axis of rotation and with a terminal point located at a point where the force is applied. And let F represent the force. Then the torque tau is simply R cross F. So imagine using a wrench to tighten a bolt. Right? So here's our bolt, here's our wrench. The torque applied to the bolt depends on how hard we push the wrench, force, and how far up the handle. So the torque increases with a greater force on the wrench at a greater distance from the bolt. So anyone who has used a wrench to tighten a bolt or loosen a bolt knows that it's really difficult if you hold a wrench down here when you try to move it, but if you hold it all the way at the end, it's a lot easier to loosen or tighten. So a bolt is tightened by applying a force of 6 newtons to a 0.15 meter wrench. The angle between the wrench and the force vector is 40 degrees. We will find the magnitude of the torque about the center of the bolt and round your answer to 2 decimal places. So we're going to assume that we're applying the force at the end of that wrench. So we want the magnitude of the torque. So this is the magnitude of the distance across the force, which is the magnitude of the distance times the magnitude of the force times sine of the angle between them. So it's going to be 0.15 meters times 6 newtons times the sine of 40 degrees. And you'll find that this is approximately 0.58 joules. And so that concludes our discussion on the cross product.